Hello, we're MAWK, and today we're going to be talking about our surgical chest tube device. These are the points we're going to talk about, such as the intro, our device, the tests we performed, and our conclusions. Our team, MAWK, is driven to provide a unique device that will aid medical personnel who are treating life-threatening injuries in high-stress environments. When we were looking at this project, we realized that thoracic trauma is common in military and civilian conditions. In the US, there are 35% trauma related deaths, and 80% of traumas are treated using a thoracostomy tube. The most common injuries of this trauma are pneumothorax and hemothorax. These happens when air or fluid enters the pleural space, thus collapsing the lung. So as you can see in this video, the surgeon is going to make a 2 to 3 centimeter incision in between the ribs. Then he would use a hemostat to dissect the subcutaneous tissue, dissecting right over the top of the rib until the next highest intercostal space is encountered. Then he punctures the tissue with the tip of the hemostat just at the top of the rib, avoiding any damage to the nerve vascular bundle at the inferior of the rib. Here, we can see the surgeon carefully entering the pleural to avoid puncturing the lungs, keeping the hemostat widely open while withdrawing it from the side to create space for the chest tube. Lastly, the surgeon will insert his or her finger, making a 360-degree twist to make sure he is at the right spot when entering the chest tube. However, as you can see, there is no real guarantee that the correct placement has been properly achieved. So after looking at all of this information, we concluded that there is a need for a device that assists in placement of a chest tube in a far forward position when there is thoracic trauma.
To solve this, we designed a miniature pressure sensor test tube device that will provide a visual indicator once the pleural cavity has been properly reached. It will secure the device inside the chest wall, avoiding any further damage to tissues or organs. The requirement traceability matrix shows the functions and tests that will be performed to the MAWK 2 calibrated tip miniature pressure sensor. It will also demonstrate the correlation between the test and the requirements as shown in the table.
So here we're going to go over the tests that we tested on the device. So first we have the BMP 180 pressure sensor test. To demonstrate the functionality of the sensor, we ordered a simple digital pressure sensor, which is the BMP 180, to test the theory. The following equipments in the picture were also obtained in order for us to basically set up the test. The ranges will be measured to ensure the pressure sensor works properly, and there is an output display of a green light also displayed. When the pressure is between 0 millimeters of mercury and 5 millimeters of mercury, a green light will be displayed alerting the operator.
The blood tip compressive stress test was performed in the makerspace using the HP series digital force gauge machine. This machine measured more than 100 newtons and no deformations occurred. The minimum needed was 20 newtons, meaning our device passed this test.
We also performed the heat deflection temperature test using the isotemp oven at UTSA to see what would be the maximum temperature our device could be exposed to without losing any functionality. We performed this at 30 degrees Celsius, which is about 86 degrees Fahrenheit, up to 72 degrees Celsius, which is about 161 degrees Fahrenheit.
So now to get into the modified insertion of device test. This test was completed with the assistance of Dr. Thomas Percival at Lackland Air Force Base. However, this test did not utilize our sensor. This test proved the testing of each component was adequate to ensure functionality in a live test subject.
So here we conducted a drop test. So basically we dropped the device at a specific height. We chose 3 different heights, which is the 4 feet, 5 feet, and 6 feet. And then basically we received the same results for each of the tries because we conducted 3 tries for each. The only difference was the first try of the 5 foot, where we saw a little bit of scratch near the tip of the device, but it really didn't affect any functionality. Another test we did, it was the weight test. So we basically used a digital scale, and we weighted the device, which came approximately to 4.209 grams, which was less than 5 pounds, meaning that it passed the weight test.
So now let's get into the overall test results. As you can see here, our device passed all tests listed with the exception of the insertion test. In the insertion test, the device did direct the chest tube properly, but did not ensure no damage to the biomedical model, therefore failing that test. Now let's take a look into our current prototype. Our product is a compact device that assists the user with proper placement of a chest tube while minimizing damage to surrounding tissue and organs. Although our device failed the insertion test and does not fully address the need, we are certain with our future improvements, our future prototypes will fully address these issues. To wrap things up, our device met most of the functional requirements discussed previously, as well as assisted the user of proper placement of a chest tube. Our device did not ensure no damage to the biomedical model, so improvements are necessary. Here are the main improvements we as a team are implementing into future prototypes. We will be modifying the blunt tip, switching the securing mechanism to a balloon, adding a one-way valve, and switching the detection sensor to the Keller miniature pressure sensor. And we would like to give a great thanks to all of these mentors listed here on this slide. They have greatly helped us and gave us wonderful feedback to get us to this point in our design process. Thank you guys so much for listening, and we'll gladly answer any questions you might have.